Bismillahirrahmanirrahim. Assalamualaikum and a very good day to you all. In this video, we are going to learn about hydrodynamic theory from the book Shitley Mechanical Engineering Design. Okay, so let's continue. Okay, theory of hydrodynamic lubrication. The present theory of hydrodynamic lubrication originated from laboratory of Beacon Tower in early 1880s in England. Okay, so you can read all the text. Beacon Tower is not a name of a tower. If you Google if you Google the name of Beacon Tower, the Google images will show a tower. No, Beacon Tower is not a building. It is a name of a person. This person that I searched the picture. This is the person called Beacon Tower. He presented the hydrodynamic theory. Okay, so okay, what is this his theory? His theory says that when you put basically this is a shaft. Okay, this is a journal. Okay, when you when he drill a hole, when he drill a hole at the middle of the journal like this to put the oil. Okay, and when the journal operates, whatever he put to plug in the hole, it fly away. Okay, it fly away. He put the corkscrew fly away. He put the wooden plug fly away. Okay, because of the pressure so high, and then whatever he put on that will fly away. So he found out that this is a recent discovery. Okay, discovery. So the explanation about this is like this. Okay, the approximate pressure distribution curve obtained by tower. Okay, this picture here on the left represents in this position. Okay, the tower in this position, meaning the pressure distribution. If you can imagine, the journal inside it is like this. When this is the bushing, this is the journal, and then it goes up and down, up and down, up and down like that. Okay, and then suppose the position is in up position, like this picture given in figure 12 and 8. Okay, okay, but it actually is going for all position. The picture in figure 12.8 give the impression that the shaft is in up position, and then when the pressure distribution is going up like that, like this picture on the left. You see, at the middle of it, the pressure is high. At the edge, left, right on the of the shaft, the pressure gradually going down, going down. And most important is when the pressure is up, it is at the middle that in this position. Yeah, the picture on the right is in this position, meaning that at one point of time when the journal is going up, okay, the pressure at is high at the middle. This is where when Buckham drill a hole at the at this drill a hole at this, he put the wooden plug fly away. He put the corkscrew fly away. So this is the new discovery. This is the place where you put the oil inside it. Okay, and remember, this is a hydrodynamic theory, meaning that the uh, the whole thing is full of lubricant, whether it is a grease, whether it is a oil, doesn't matter, but it is a full of lubricant. Okay, so try to understand these three slides that I try my best to explain. Okay, uh, and then you can grasp the concept of hydrodynamic theory. So Osborne Reynolds, okay, the result obtained by Tower has such regularity that Osborne Reynolds conducted conclude that there must be a definite equation relating to uh, the friction, the pressure and velocity. meaning that Osborne Reynolds and Beacon Tower live at the same era. Okay, they are both scientists living in the same era and same generation. So, okay, they use each other's finding. Okay, so you are familiar with Reynolds number in fluid mechanics. Okay, when you learn fluid mechanics, you will see, uh, you will learn a lot about Reynolds number, and in this slide also, in this chapter also, you will learn again about Reynolds number. Okay, so Reynolds number derive an equation for the theory of lubrication based on Reynolds number following the experiment by Tower. Okay, Tower do the experiment, Reynolds do the mathematical about it. Okay, so uh, solution is challenging problem that many interest, many investigations ever since then. It is a starting point of lubrication studies. Okay, in that of over 100 years, people have done research, ongoing research on lubrication and everything. Okay, so this is the Reynolds assumption. Okay. Reynolds picture the lubricant as adhering to curved surface vapor by removing surface into a narrowing wedge shape to create a fluid of film pressure. What is a wedge shape? You go back to the picture, figure 12.8, the up. Okay, when the pressure, when the shaft is going at up position, the pressure is going up, like the picture in figure 12.8. Okay, you can pause the video, go back to figure 12.8. You can see the wedge position. Okay, so this is an assumption made by Reynolds. The lubricant obeys Newton's Vickers effect. Okay, the forces due to inertia is neglected. Lubricant assumed to be incompressible. Viscosity is assumed to be constant throughout the film. Pressure does not vary in the x direction. Okay, this is number 5. They are number 6, number 7, number 8 in the next slide. I want to explain this first. Okay, Newton Vickers effect, meaning that flowing smoothly. Force due to inertia in lubricant are neglected. However, in reality, when it is moving, always have force, but we assume can be neglected. Okay, lubricant is assumed to be incompressible. In reality, uh, when you compress water, you compress lubricant can become shortened and everything. So like deformation uh, of, of anything. Okay, of course it can be deformed, but we assume it's incompressible. Viscosity is assumed to be constant. Of course, when do is heating time, uh, when exposed to heat, exposed to temperature, viscosity will gradually become lower. Okay, become no viscosity. Okay, again, assumption is constant, and pressure does not vary in x direction. X direction is like this. Okay, this is direction, the flow like this. This is an x direction. Of course, it varies. Okay, but it's we assume to be not vary to make an mathematical equation for it. Okay, so Reynolds assumption on general bearing. Number 6, bushing and general extended infinitely in z direction. Mean there is no lubricant flow in z direction. Meaning that number 6, meaning that it assume this journal is infinite left, infinite right. Okay, no lubricant flow, meaning that lubricant doesn't go out in the left, doesn't go out in the right. Okay, filler pressure is constant in y direction, uh, and thus the pressure depends only on coordinate x, meaning that the filler pressure, this is x y coordinate. Okay, constant. This is the filler pressure constant. Velocity of any particle, it depends only on coordinates x and y. Okay, no coordinate z. Just in because we imagine this is as xy axis, uh, just for making an make to make an equation, we just assume it is an xy axis. Okay, so you see here, let me explain about this picture, picture 12 and 9. Okay, this is a partial bushing, meaning that before it going into full bushing, full bearing, meaning that when full bearing is it is full of lubricant. Okay, when the flow come here, when you put the lubricant inside the journal, while it is going to become full, it is partially full. It is partially full. And when it is partially full, this equation, we will do this equation. Okay, you see here, the flow is going here. The flow is assumed to be one direction. Okay, and then this is a particle, one particle. If you can take, you can imagine one particle take one element, molecule of lubricant. Okay, and then you see here the uh, the force impacted on P here is area, P equals to F over A. Okay, the equation is originated from normal equation, P equal to F over A. So A is the dy dz. Okay, it is actually in area, and then you can get force and everything. Okay, get force and everything. This is because the flow impacted the give effect to the this surface on the right. The equation is this. You try to relate this equation to this equation. Okay, the area is dy dz. It is the area, and the equation is originate from here. And then you see here from the bottom and from the up, there is a shear stress. Okay, shear stress, of course, because the particle going like that. Okay, so there is the element of shear, the shear dy dz. Okay, so shear dz dx dz. Okay, and then this is the element of force plus the shear, because when the flow is flowing, you can imagine one particle, use a big, take one particle, imagine you take one molecule of lubricant. Lubricant is like that, and the flow is like that, flow going like that. This is how the you assume the theory of lubricant. This is how they make the theory. You assume the theory happen like that. Okay. So and then this is the rotating journal, like my marker pen is rotate like this. This is the rotating journal. Okay. U is the velocity of the lubricant coming flowing. Velocity of lubricant. Okay, coming from the left to the right. So that is how you understand the theory. And summing forces in x direction give this equation. Okay, and then you get u equals to this equation, constant everything. You integrate, and then you get c constant 1, constant 2, everything. Okay, okay. Now that the act of holding x means that constant 1, constant 2 can function of x, so assume there is no slip between lubricant. Okay, and then two set of condition, values evaluating c1 and c2, you get this, and you get this equation u. U is the velocity of the lubricant flowing. Okay, velocity of lubricant flowing. Okay. If you want to understand what is the difference between capital U and small u, there is a video I made in the among the earlier video on chapter 12, uh, okay, stating what is capital U and what is small u. Okay. Okay, this equation gives the velocity distribution of the lubricant film as a function of coordinate y and pressure gradient dp over dx. Okay, and then okay, you can read all this, and then when the pressure is maximum, dp dx equals to 0, and velocity equals to u equals to u over h y. U is the velocity of the fluid. Okay, small u is velocity of the lubricant. Capital U is the velocity of the journal. Okay, of the journal moving, and H is the thickness. Okay, thickness of the lubricant. Okay, meaning that if you can imagine this is the journal, you can imagine this is a journal. This is a gap between the bottom of the bushing and the journal. Let's say this is the gap. You can see here the gap. Okay, that is H. Okay, this H is so small you cannot see with your eye. Okay, but for to make an explanation of the theory, the picture is made as a big one, big gap, but actually is no gap. Okay, actually gap is very minimum, you cannot see with your eye. Okay, uh, because of the weight of the shaft itself. Okay, and y is the any point. Okay, any point from the, this is the journal, this is the base of bushing, this is h, and this is y. Y is any point from, if you take this point, this is y, this is y, and everything at any point from the below until the journal. Okay, we next we define q as the volume of lubricant flowing, okay, in x direction per unit time. Okay, now we want to find the volume of lubricant. Okay, so this is the q, the volume of lubricant. So 0 from about to h is, this is the way mathematics says about how to fill something. Yeah, this is the integration. uh, okay, integration. Okay, so if we want to say the position be from 0 up until in full position. Okay, okay, now is the position I want to explain about the term 0h. What does it mean in real life? Okay, mathematically it says 0 over h, 0 until h, the limit 0 until h. Okay, when you are, let's say you are pouring water. Okay, you take and you pour water inside a container. Okay, it begin with 0, nothing inside, nothing inside here first, and then gradually when you are, the limit is 0 and the h is here. Okay, and when you pour water inside here, it is from the limit 0 until gradually go up until h limit. Okay, this is the h limit. The same goes, it can apply to this general bearing. You can apply to this explanation. What is the meaning by 0? What is the meaning by h? H is the full capacity of the journal, meaning that the journal is full of lubricant. Okay, while it is being full, it it is a flow. Okay, the unit flow of lubricant. Okay. Okay. Next step is assumption of incompressible lubricant and state that the flow is the same for any cross section. Okay, so when the flow is full, the journal is full, no flow, no flow anymore. Okay, okay, when the journal is full of lubricant, no lubricant flowing anymore. Assume that no going up, no going in, coming in. Okay, so no lubricant, no lubricant coming in, coming out. Okay, so for the equation, can get this equation for this is a classical Reynolds equation for one-dimensional flow. Side leakage, if it neglects side leakage, with the flow in the z direction. Okay, this is side leakage. Of course, there is side leakage in reality, but we assume no side leakage. Here, left and right. Okay, no side leakage. So, the question is 6u dh per dx. Okay, and then is no general analytical location in equation 12.1. So, approximate solution has been obtained by electrical analogies, mathematical estimation, realization method, numerical and graphical method. One important solution is due to Sommerfeld, which is expressed in the form of R over C F equal to theta R over C power 2 U N micro N P. Okay, this is the Sommerfeld number. You will learn better in the next video, okay, about this number, and we are going to do a long exercise doing this. Okay, so this equation is Sommerfeld number. We will do a lot of exercise of this. Okay, and the solution is so long to solve this equation. Okay, that's all for the video today. We are going to continue in the next video on design consideration. Okay, thank you very much.